What if we could leave the solar system never to return? The idea may seem impossible, but the truth is, once we venture far enough, the journey becomes one way. From the sun's fading light to the cold emptiness of interstellar space, each step away brings us closer to the unknown and farther from home. Join us as we explore the science, the physics, and the incredible challenges of venturing beyond the stars. Don't forget to like, subscribe, and hit the bell to join us on this cosmic adventure. Stay curious, and let's dive into the mystery of leaving the solar system. At the farthest known reach of the sun's outward pressure, the solar system meets a surrounding environment that does not belong to the sun at all. Here the familiar idea of planetary space gives way to a boundary made not of rock or ice, but of motion, pressure, magnetic fields, and very thin gas. The region is dark, cold, and diffuse. It contains almost no solid bodies large enough to define it by shape. Its structure is instead set by the contest between material flowing out from the sun and material already present between the stars. This is the edge of the sun's active domain, the place where its expanding influence no longer pushes freely into the galaxy. The sun constantly releases a stream of charged particles called the solar wind. A charged particle is an atom or subatomic particle carrying electric charge, and because of that charge it responds to magnetic fields. This wind moves outward in all directions, carrying with it part of the sun's magnetic field. Near the planets, that flow is one of the basic conditions of space. Far beyond the planets, it still continues, though it becomes thinner and weaker as it spreads across a greater volume. It does not travel into emptiness. It moves into a wider galactic environment already occupied by rarefied gas, dust, and magnetic fields. The place where the pressure from the solar wind can no longer dominate that surrounding medium is the distant edge of the sun's outward control. This outer boundary is not a clean shell like the surface of water or the wall of a vessel. It is a transition region shaped by balance. On one side lies space still mostly governed by the outflow from the sun. On the other lies the local interstellar medium, the thin matter between stars in this part of the Milky Way. The word medium here means the material filling a region, however sparse it may be. In ordinary life, a medium might be air or water. In this far outer setting, it is an extremely thin mixture of gas, charged particles, dust grains, and magnetic structure spread through interstellar space. Even though it is thin beyond everyday comparison, it still has pressure, and over immense distances that pressure matters. The boundary between the solar wind and the interstellar medium is known as the heliopause. It marks the place where the outward push of the solar wind is balanced by the inward pressure of the surrounding interstellar material. Observations from the Voyager spacecraft indicate that this boundary is real, measurable, and dynamic. It is not fixed at one exact distance in all directions. It shifts with solar activity and with the shape imposed by the sun's motion through the local galaxy, as well as by the magnetic field outside. The heliopause is therefore less like a perfect sphere and more like a broad, uneven frontier. It encloses the heliosphere, the large bubble carved out by the solar wind. At this extreme distance, sunlight still travels outward, and the sun is still visible as a star, but light alone does not define possession. Gravity also extends outward without a final wall, weakening gradually with distance. Because of that, this boundary does not mean that the sun's gravity ends here. It means something more specific. It marks the end of the sun's ability to maintain a dominant bubble of outward flowing plasma around itself. Plasma is hot gas in which electrons and atomic nuclei move separately rather than remaining bound together as neutral atoms. The heliopause is therefore a plasma boundary, not the absolute end of the solar system in every possible sense. This distinction is important. An object may cross beyond the heliopause and enter interstellar space while still remaining, for a very long time, within the much broader gravitational influence of the Sun. The conditions near this boundary are subtle rather than dramatic. There is no visible wall, no bright line appears in the darkness. The change is detected through instruments that measure particle populations, magnetic field behavior, and local plasma properties. When Voyager 1 crossed this frontier in the year 2012, and Voyager 2 in the year 2018, the evidence came through shifts in energetic particles from the Sun, changes in cosmic ray levels arriving from outside the heliosphere, and differences in the surrounding plasma. Cosmic rays are very energetic particles moving through space, many of them originating far beyond the solar system. Inside the heliosphere, the Sun's magnetic environment helps block part of their flow. Beyond the heliopause, that shielding weakens. The region outside becomes more directly representative of the galaxy beyond the Sun's bubble. Even here, however, the border remains complex. Observations indicate that the magnetic field direction on either side of the heliopause does not always change in a simple, dramatic way. The transition includes layered behavior and local structure. The outer edge is shaped by the Sun's cycle of activity, by variations in solar wind pressure, and by conditions in the local interstellar medium itself. It remains uncertain in detail how all parts of the heliosphere are shaped far from the Sun, especially in directions not directly sampled by spacecraft. Models differ in some features of the outer form, including how much the local interstellar magnetic field distorts it. What is known is that the heliopause exists as a meaningful physical boundary, and that beyond it lies a region no longer filled and governed mainly by the Sun's outward wind. The scale of this frontier is difficult to hold in the mind. It lies far beyond Pluto and far beyond the main planetary realm. Distances here are often described in astronomical units, with one astronomical unit equal to the average distance between Earth and the Sun. By the time the Voyager spacecraft crossed the heliopause, each was more than 100 astronomical units from the Sun. At such distances, the Sun's warmth has long since faded into a weak radiance, and the ordinary markers of home have vanished. Yet the significance of the boundary is not emotional or symbolic. It is physical. It marks the end of one environment and the beginning of another. This outermost frontier also reveals something quiet about the solar system itself. The solar system is not a sealed container sitting apart from the galaxy. It is an open system immersed in galactic surroundings. The Sun pushes outward and creates a temporary protected cavity. But that cavity moves through the Milky Way and is continually pressed upon by external matter and fields. The edge is therefore a place of exchange. Neutral atoms from interstellar space can drift inward. Dust can pass across large distances. Energetic particles can be blocked, guided, or admitted depending on conditions. The boundary does not isolate the solar system completely. It only marks where the Sun ceases to dominate the local space in the same way. In that sense, the edge of the Sun's reach is not an ending with a sharp final line. It is the limit of an active claim. Beyond it, the Sun remains present as a source of light and gravity, but no longer as the unquestioned architect of the surrounding medium. The outward wind that once defined local space has spent its force against the pressure of the galaxy. From there onward, interstellar space is no longer an idea beyond the solar system. It is the immediate environment. The heliosphere is the large, extended bubble formed by the solar wind as it expands outward from the Sun into the surrounding interstellar medium. In broad terms, it is the volume of space where that outward flow still establishes a distinct solar environment, even far beyond the planets. Its existence means that the solar system is not only a family of worlds orbiting a star, it is also a vast moving cavity in the galaxy, defined by flowing plasma, magnetic structure, and continuous exchange with the matter beyond it. The heliosphere is not seen directly as a glowing shell. It is inferred and measured through particles, fields, and the behavior of atoms moving across its boundaries. At its simplest, the heliosphere can be imagined as the Sun's atmosphere extended across enormous distance, though this comparison is only partial. An atmosphere on a planet is held mainly by gravity and composed of neutral gas. The heliosphere, by contrast, is created by a stream of charged particles released by the Sun and guided by magnetic forces. The solar wind carries the Sun's magnetic field outward, stretching it into a large three-dimensional structure. As the Sun moves through the local interstellar medium, this structure does not remain perfectly round. It is shaped by both internal pressure from the solar wind and external pressure from the galactic surroundings. For many years, the heliosphere was often pictured as something like a comet, rounded at the front and trailing far behind in a long tail. That picture captures one important truth. The Sun is moving through the local interstellar medium, and that motion matters. Just as air shapes the flow around a moving object, the interstellar medium influences the form of the heliosphere. The front side, facing the direction of motion, is compressed. The opposite side is drawn out into a more extended wake-like region often called the heliotail. This general asymmetry remains useful. Yet observations and models now indicate that the true shape is more complex than the older smooth comet image suggests. The heliosphere appears to be uneven, dynamic, and structured by magnetic forces more strongly than simple early pictures implied. Data from missions such as Voyager, Cassini, New Horizons, Ulysses, and the Interstellar Boundary Explorer have shown that the outer heliosphere does not behave like a stable, uniformly inflated bubble. The local interstellar magnetic field seems to distort it. Variations in the solar wind during the solar cycle appear to make it expand and contract. Models suggest that some regions may be more rounded than once expected, while others may contain ripples, folds, or broad asymmetries. In this context, a ripple is a large-scale variation in the surface rather than a smooth, unbroken contour. The heliosphere therefore breathes, shifts, and responds. Its form is also difficult to know with certainty because no spacecraft has travelled around it and mapped it fully from outside. The picture comes from a combination of local measurements and remote sensing. Local measurements are taken where spacecraft pass through particular regions. Remote sensing comes from observing energetic neutral atoms, which are particles created when charged particles exchange charge with neutral atoms and then travel in straight lines that can be detected from afar. These observations have given scientists broad views of the heliosphere's structure, including evidence that it is not simple, not symmetrical, and not static. Even so, some features remain unsettled. Observations indicate the overall bubble is real and bounded, but it remains uncertain exactly how long, broad, or tail-like every part of it may be. Within this great bubble, the Sun's magnetic influence is carried outward by motion rather than by stillness. The magnetic field of the Sun is twisted by rotation, stretched by the flowing solar wind, and folded into large patterns across interplanetary and outer heliospheric space. These magnetic structures affect how charged particles move. They shape how solar particles travel outward and how galactic particles attempt to move inward. In this way, the heliosphere acts partly as a shield. It reduces the intensity of some incoming cosmic rays from the galaxy, though it does not block them completely. The amount of shielding changes with solar activity, because the strength and structure of the solar wind and magnetic field also change. This means the heliosphere is not just a boundary object, it is a living volume of interaction. The solar cycle, which rises and falls over roughly 11 years, changes the character of the wind flowing from the sun. Stronger and weaker phases alter pressure throughout the heliosphere. Disturbances launched from the inner solar system can take long periods to travel outward, but they eventually affect the outer shape and internal conditions. What seems distant and detached is in fact linked to the changing activity of the sun. Over time, the heliosphere contracts and expands in response. Its outer surfaces shift, and the locations of key transitions are not permanently fixed. The heliosphere also moves with the sun through the Milky Way. It is not standing still while the galaxy flows around it. The sun travels through a local cloud of interstellar material, and the heliosphere meets that material continuously. Neutral interstellar atoms can drift inward because they are not guided in the same way as charged particles. Some later become ionized and are then caught up in heliospheric processes. Interstellar dust can also enter. At the same time, solar material flows outward. The heliosphere is therefore a region of filtering rather than of perfect separation. It divides environments, but it also permits exchange. Its size is immense by planetary standards. All the major planets orbit deep inside it. Even the Kuiper belt lies far within the Sun's heliospheric bubble. Yet size alone does not explain its importance. The heliosphere defines the physical setting in which the planets exist, as part of a stellar system, rather than as bare objects exposed directly to the full galactic environment. Earth and the other planets move inside this protective, changeable cavity. Conditions within it are shaped first by the Sun and only secondarily by the galaxy beyond. Without the heliosphere, the particle environment of the solar system would be profoundly different. Still, the heliosphere is not the whole solar system in every sense. It is one way of defining the Sun's domain, based on plasma and magnetic influence. That distinction matters because the shape of this bubble tells a different story from the shape of the Sun's gravity. Gravity extends much farther and declines gradually rather than ending at a surface. The heliosphere instead has a meaningful outer form because it is produced by flow-meeting resistance. It has a front, flanks, and a trailing region. It can be compressed, distorted, and stirred. It can hold broad structure because it is a moving interaction between the Sun and the galaxy. Seen in this way, the heliosphere is the true outer weather system of the solar system. It is vast, thin, and almost invisible, yet full of organized behavior. It surrounds the known planets, carries the changing influence of the Sun across great distance, and gives the solar system a real outer shape as it moves through interstellar space. Far inside the outer boundary, but still at immense distance from the Sun, the solar wind begins to lose the free, swift character it carries through most of the solar system. This is the frontier where the outward flow first encounters enough resistance from the surrounding interstellar medium that it can no longer continue in the same way. Until this point, the solar wind moves faster than the speed at which pressure disturbances travel through that plasma. In that condition it is called supersonic. Here the word does not refer to ordinary sound in air, but to the speed of pressure waves in ionized gas. When the solar wind crosses this threshold, it must slow, compress, and change state. That transition marks one of the most important frontiers in the outer heliosphere. This region is known as the termination shock. A shock is a narrow transition across which physical conditions change abruptly. In everyday experience, a shock wave may be associated with thunder or an explosion. In space plasma, it is not heard and not seen as a bright wall, but it still reorganizes speed, density, temperature, and magnetic structure. At the termination shock, the solar wind drops from supersonic flow to slower, subsonic flow. Subsonic means that pressure changes can now travel through the plasma fast enough to influence the flow ahead and around obstacles. Beyond this point, the solar wind does not stop. It continues outward, but it moves differently. It becomes hotter, denser, and more disturbed. The existence of this transition follows from the simple fact that the solar wind cannot expand outward forever without meeting the pressure of its surroundings. Close to the Sun, the wind is strong enough to drive past local variations and carry the solar magnetic field outward in a broad expanding stream. Over great distance, that same wind thins as it spreads, its pressure falls. Meanwhile, the interstellar medium presses inward through its own gas pressure, magnetic pressure, and the effect of the Sun's motion through the galaxy. Eventually, the outward flow must respond. It does so first not at the heliopause itself, where balance is finally reached, but earlier, where the wind is forced to give up its supersonic state. The termination shock is not believed to be a perfect fixed surface. It is broad in overall scale, irregular in detail, and variable over time. The level of solar activity changes the pressure supplied by the solar wind, and that can move the shock inward or outward, because the heliosphere itself is asymmetric. The distance to the termination shock differs in different directions. Measurements by Voyager 1 and Voyager 2 support this picture. The two spacecraft encountered the shock at different distances from the Sun, showing that the outer solar wind frontier is not evenly shaped. This difference is understood as part of the larger asymmetry of the heliosphere, influenced by solar conditions and the local interstellar magnetic field. As the solar wind crosses this shock, the change is not merely a slowing of bulk motion. Energy is redistributed. Some of the directed outward flow is converted into heat and into the energizing of particles. The plasma becomes more turbulent. Its magnetic field becomes more compressed and variable. Particles can be accelerated in this region to higher energies. This is one reason the outer heliosphere is scientifically rich. It is not a silent drift into emptiness, but an active transition where plasma physics unfolds across a region too large for ordinary intuition. The outer solar system here becomes a place of interaction rather than simple outward expansion. Beyond the termination shock lies the heliosheath, the broad region in which the slowed solar wind continues toward the heliopause. In this section, however, the focus remains on the frontier itself, on the moment where the wind first yields. The termination shock marks the end of the solar wind as a freely supersonic stream. It is the place where the Sun's outward breath meets enough opposition that the character of the flow changes fundamentally. This makes it one of the true turning points in any outward journey. A spacecraft passing through it does not cross a visible gate, but it enters a region where the physical behavior of space is no longer the same as it was within the inner heliosphere. The crossing is detected not through sight, but through instruments that register sudden differences in particles, plasma, and magnetic field. Voyager 2, which carries a functioning plasma instrument, provided especially valuable direct evidence of the shock crossing. It measured a clear slowing of the solar wind and changes in temperature and density consistent with the expected transition. Voyager 1, whose plasma instrument was no longer operating, detected the crossing through other changes in the local environment, including energetic particles and magnetic behavior. Together, these measurements confirm that the termination shock is not merely a theoretical feature. It is a real and measurable boundary within the Sun's outer domain. Even so, not every detail is settled. Space plasma at these distances is collisionless, which means ordinary particle-to-particle collisions are too rare to control the transition in the way they would in dense gas. Instead, electromagnetic forces and collective plasma behavior govern the shock. This makes the structure more complex. Observations indicate that pickup ions, which are particles created when neutral atoms drifting in from interstellar space become ionized and join the solar wind, may play an important role in the energy balance near the shock. It remains uncertain in detail how energy is divided there under all conditions, and how the shock behaves across the full heliosphere in different phases of solar activity. What is clear is that the transition is extended, dynamic, and shaped by more than simple compression alone. The termination shock also changes the meaning of distance. Within the inner heliosphere, a spacecraft moving outward still travels through a region where the solar wind behaves as a relatively direct extension of the Sun. Beyond the shock, that directness is gone. The wind has been forced into adaptation. It slows, piles up, and begins to bend in response to the pressures surrounding the heliosphere. In this sense, the frontier is not only a physical threshold but also a shift in regime. The rules are not entirely new, but they are no longer the rules of free expansion. The great importance of this frontier lies in its quiet finality. Once the solar wind has crossed the termination shock, the Sun's outward flow has already surrendered one of its defining qualities. It still moves, still carries solar material and magnetic influence, but it no longer races outward unchecked. The long journey from the Sun has met resistance that cannot be ignored. The outer darkness is no longer merely empty distance. It has become an opposing environment, and the solar wind has begun to yield to it. Beyond the heliopause, the surrounding environment is no longer shaped mainly by the solar wind. It belongs instead to the local interstellar medium, the sparse matter that occupies the space between stars in this region of the Milky Way. This medium is not empty. It only appears empty when judged by ordinary human scale. In physical terms, it contains gas, dust, magnetic fields, and energetic particles spread thinly across enormous distance. Its density is so low that even the best terrestrial vacuum remains far denser. Yet over distances measured in trillions of kilometers, this faint material becomes the substance through which stars move, clouds form, and galactic structure persists. Outside the heliosphere, a spacecraft begins to travel not through the Sun's outward-made cavity, but through the ambient material of the galaxy itself. Most of the matter in this local interstellar medium is gas, mainly hydrogen, with a smaller amount of helium and traces of heavier elements. Some of that gas is ionized, meaning that electrons have been stripped from atoms, leaving charged particles. Some remains neutral. The proportion changes from place to place depending on temperature, radiation, and local history. This nearby region around the Sun is thought to be part of a warm, partially ionized cloud embedded within a larger galactic environment. Warm here is only a technical term. It refers to temperatures high enough that particles carry substantial energy, not to anything like bodily warmth. Because the density is so low, even gas at thousands of degrees does not transfer heat in the familiar way. It remains a tenuous medium, not a furnace. The local interstellar medium also contains dust, though in very small amounts. Dust grains in space are tiny solid particles made from heavier elements such as carbon, silicon, oxygen, and metals combined into minerals, ices, or carbon-rich material. These grains are mixed through the gas and move under the influence of gravity, radiation, and magnetic effects. In denser interstellar clouds, dust helps block and redden starlight. In the local region around the Sun, dust is present but sparse. Even so, it matters. A spacecraft traveling outward at high speed does not move through absolute emptiness. Over immense time, rare impacts from tiny grains become part of the physical reality of interstellar travel. Another basic feature of the local interstellar medium is its magnetic field. The galactic magnetic field in this nearby region is weak, but not negligible. Because charged particles respond to magnetic structure, this field influences how plasma moves, how cosmic rays propagate, and how the heliosphere itself is shaped from outside. The interstellar magnetic field is one reason the heliosphere is distorted rather than perfectly symmetric. Beyond the heliopause, this magnetic environment becomes a direct condition of space instead of an external influence pressing on a solar boundary. It is part of the normal fabric of the region. Cosmic rays are also a defining presence here. These are high-energy particles moving through the galaxy, produced by energetic astrophysical processes such as supernova remnants and perhaps other violent environments. Inside the heliosphere, some of these particles are partially modulated, meaning their flow is altered by the magnetic and plasma structure created by the Sun. Outside the heliopause, that filtering effect is reduced. A spacecraft enters a region where the galactic particle environment is more direct. Measurements from the Voyager spacecraft show this clearly. After crossing the heliopause, the detected intensity of galactic cosmic rays rises, while energetic particles associated with the Sun decline. This change helps mark the passage from solar-dominated space into interstellar space. Even in this region, however, the word interstellar can be misunderstood if imagined as a dramatic separation between stars. The local interstellar medium is not a void with occasional isolated objects floating in it. It is a continuous, structured substance on galactic scales. Its density is low, but its presence is constant. It carries memory of stellar life cycles, gas expelled from old stars, enriched by earlier generations of stellar evolution, mixed by supernova shock waves, and shaped by galactic motion contributes to its composition. The matter between stars is not unused matter, it is recycled matter. It belongs to the long exchange through which stars are born, evolve, and return part of themselves to the galaxy. The Sun moves through this medium. It does not remain fixed while the interstellar material stands still. This means the local conditions around the heliosphere can change over very long time spans as the Sun passes through different interstellar environments. Some regions of the galaxy contain denser clouds, others are more rarefied. The properties of the surrounding medium therefore help determine the size and shape of the heliosphere. Observations indicate the Sun currently travels through a relatively low-density local cloud, but the exact structure of this neighborhood remains an active area of study. It remains uncertain in detail how sharply different nearby interstellar clouds are separated and how conditions may vary along the Sun's path over long periods. For an outward journey, the local interstellar medium changes the meaning of destination. To leave the heliosphere is not to leave all environment behind. It is to exchange one environment for another. The new one is not created by the Sun, and it does not respond primarily to solar cycles or the direct outward flow of solar plasma. Instead, it reflects the broader condition of this arm of the Milky Way. A traveller moving through it is surrounded by matter that is not part of the active solar wind system. The gas may be thin beyond intuition, but it is galactic in origin and galactic in context. This region also reveals why the phrase leaving the solar system can mean different things depending on what is being measured. In terms of plasma environment, crossing the heliopause places a spacecraft in interstellar space. In terms of gravity, the Sun's influence extends much farther. A craft beyond the heliopause may still be on a path that remains gravitationally bound to the Sun unless it has enough speed to escape entirely. The local interstellar medium therefore begins before the Sun's gravity becomes irrelevant. This overlap is one reason the outer solar system is conceptually subtle. Interstellar space is reached before solar gravity has fully lost practical meaning. Yet none of this reduces the importance of the transition. Outside the heliosphere, the outward traveller moves through the actual material between stars. The Sun remains visible, still powerful in light and still significant in gravity. But the surrounding medium is no longer the Sun's own. The local interstellar medium becomes the immediate reality thin gas, sparse dust, quiet magnetic structure, and energetic particles passing through the dark. The space between the stars is not empty silence. It is a real physical environment, and the solar system is immersed within it. Far beyond the recognized planetary realm, beyond the Kuiper belt and beyond the last major orbits of known dwarf worlds, there is thought to be a vast outer reservoir of icy bodies surrounding the solar system. This is the Oort cloud. It has never been seen directly, and its existence is inferred mainly from the orbits of long-period comets and from dynamical models of solar system formation and later gravitational evolution. Observations and models indicate that it forms a broad, roughly spherical outer shell of icy objects loosely bound to the Sun, extending to distances far greater than those of the planets, and reaching into a region where the gravity of passing stars and the wider Milky Way begin to matter in a serious way. NASA describes it as a giant spherical shell surrounding the Sun, planets, and Kuiper belt objects, and places it broadly between about 5,000 and 100,000 astronomical units from the Sun, while ESA materials likewise describe it as the distant source of many long-period comets, and note that its outer reaches may extend a substantial fraction of the way toward the nearest star. At this margin, the solar system becomes less like a structured set of nested orbital zones, and more like a deep gravitational haze of ancient remnants. The objects thought to populate the outer Oort cloud are small, dark, and icy, composed of materials left over from the cirra of planet formation and later scattered outward by interactions with the giant planets. They are not arranged in a thin disk like the Kuiper belt. Instead, the outer cloud is generally understood as approximately spherical, with bodies moving on orbits in many directions and with periods so long that a single revolution can take hundreds of thousands or even millions of years. ESA and NASA both present the Oort cloud as a reservoir of comet-like icy bodies left from the solar system's formation, and ESA notes that some observed comets from this reservoir return to the inner solar system only after immensely long orbital intervals. The outer margin of the Oort cloud is important because it approaches a region where the Sun's hold becomes very weak. Gravity does not stop, but it declines with distance, and here the binding of objects to the Sun is easily disturbed. Passing stars, the tidal pull of the Milky Way, and encounters with dense interstellar structures can alter the orbits of these distant bodies. NASA states that the outer extent of the Oort cloud is where the Sun's gravitational influence can be overpowered by that of other stars, and ESA notes that close stellar passages can perturb Oort cloud objects and send some inward toward the planets. The result is a region that still belongs to the solar system in a broad dynamical sense, yet does so only tenuously. It is a zone of possession by weakness rather than by control, because no object in the Oort cloud has been directly imaged in place. Much about its detailed structure remains uncertain. NASA explicitly notes that no objects residing within the Oort cloud have ever been directly observed. The inner and outer boundaries are therefore model-based rather than sharply measured. Different summaries place the cloud's extent somewhat differently, with NASA giving a broad range of about 5,000 to 100,000 astronomical units, while ESA educational material describes an outer Oort cloud extending to roughly 20,000 to 200,000 astronomical units and an inner, more flattened component extending inward to a few thousand astronomical units. These differences do not mean the idea is doubtful. They reflect the fact that the Oort cloud is inferred indirectly, that its population is sparse and distant, and that its boundaries are expected to be gradual rather than crisp. What is known is that long-period comet orbits strongly support the existence of a distant reservoir. What remains uncertain is the exact population, detailed structure, and full radial extent of that reservoir. The physical character of the outer Oort cloud is quiet and sparse. Sunlight at those distances is extremely weak. The sun itself would still outshine the surrounding stars, but it would no longer dominate the sky in any familiar way. Temperatures remain low enough for volatile ices to survive over long timescales, which is why the bodies there are thought to preserve primitive material from the early outer solar system. NASA and ESA both frame the Oort cloud as a storehouse of icy comet-like objects, and comet science within both agencies connects this distant reservoir with some of the least thermally processed material available from solar system history. The outer margin, then, is not only a boundary of distance, it is also a deep archive of cold matter that has changed little since the early rearrangement of the giant planet system scattered it outward. In this region, the meaning of leaving the solar system becomes more subtle than it appears closer to the Sun. A spacecraft might already have crossed the heliopause and entered interstellar space in terms of plasma environment, yet still be far inside the broader gravitational domain of the Sun. The outer Oort cloud shows how wide that gravitational domain may be. It also shows how weak it becomes. To travel through this margin is not to move through a crowded frontier of worlds. It is to pass through an immense shell of scattered remnants so distant and so lightly held that the galaxy itself begins to compete for them. At that scale, return is no longer prevented by a wall, it is defeated by distance, by orbital times that stretch beyond human timescales, and by the fact that the Sun's authority here has thinned into a fragile claim. Farther inward from the most weakly held edge of the Oort cloud lies a region thought to contain a greater concentration of distant icy bodies, still profoundly remote, but more firmly retained by the Sun than those at the outermost margin. This region is often called the inner Oort cloud, and in some discussions it is referred to as the Hills cloud after the astronomer Jack Hills, who proposed that a denser inner reservoir may exist and help supply the long-period comets that later appear from the more weakly bound outer cloud. It has not been directly observed, like the broader Oort cloud itself. It is inferred from comet behavior and from models of how small icy bodies are scattered, stored, and disturbed over long timescales. In this inward region, the solar system is still diffuse and dark, but the Sun's pull is no longer quite so fragile. It remains weak by ordinary planetary standards, yet it is more persistent, and that persistence changes the nature of distance. The inner Oort cloud is thought to begin well inside the main outer shell, and to extend outward through a broad range of space. Different models place its inward limit differently. Some descriptions place the main inner edge of the broader Oort region at around 1,000 astronomical units, while others suggest a more gradual inward extension. This uncertainty reflects the fact that the structure is theoretical rather than directly mapped. There is no known sharp wall separating inner cloud from outer cloud. Instead, the population is generally understood as changing gradually with distance, with the more tightly bound inner population blending outward into the looser, more easily perturbed bodies of the outer cloud. The region exists as a dynamical idea, meaning it is defined by how objects move and remain bound, rather than by direct visible boundaries. What distinguishes this inner reservoir is not brightness, for it remains unlit except by very weak sunlight, and not density in any human sense. For the spacing between objects is still immense. Its distinction lies in orbital binding. Objects here are expected to have smaller semi-major axes than those in the outer cloud. A semi-major axis is the basic measure of an orbit's size, equal to half the longest width of an ellipse. Smaller semi-major axes mean orbits that are, on average, more tightly held to the Sun and less easily stripped away by the gravitational influence of passing stars. The galaxy still matters here. The tidal force of the Milky Way and occasional stellar encounters can still alter these distant paths. But the Sun's claim is stronger than it is at the outermost edge. These bodies are less exposed to immediate loss and more likely to remain a long-term deep reservoir. This has an important consequence for the long history of the solar system. The inner Oort cloud may preserve a population of icy bodies that have remained stored over billions of years, disturbed only occasionally and incompletely. In some models, this inner storehouse acts as a source that can refill the outer cloud after the outer population is reduced by stellar passages and galactic tides. That makes the inner cloud not merely an inward continuation, but a stabilizing depth to the solar system's most distant comet reservoir. It is a place where the Sun's gravity is still weak enough to allow very long orbital times and great sensitivity to outside influence, yet still strong enough to hold material over cosmic timescales with greater reliability than at the fringe. The physical conditions remain deeply quiet. Sunlight is reduced to a faint illumination scarcely stronger than starlight would seem from Earth if the Sun were not present. The thermal environment is extremely cold, preserving volatile ices that nearer the Sun would long since have changed state or been lost. The bodies themselves are expected to be small and dark, composed of mixtures of water ice, other frozen compounds, dust, and rock. They are relics of early solar system history, scattered outward long ago by gravitational interactions with the giant planets during and after planetary formation. In this sense, the inner Oort cloud is not built in place. It is an archive of displacement. Its contents are former inner members of a much more compact young solar system, exiled outward and stored at astonishing range. Time in this region becomes difficult to understand in ordinary terms. Orbits here may still take hundreds of thousands or millions of years, though generally less extreme than those of the most distant outer cloud bodies. Motion exists, but it is stretched so greatly that a human life offers no natural measure of it. A body in the inner Oort cloud does not circle the Sun in any way that resembles the movement of planets. It spends vast spans of time in cold darkness, changing position only slowly against a backdrop of stars that themselves shift over galactic time. Return from such distance is not impossible by law, but it becomes detached from practical meaning. The scale alone defeats ordinary notions of travel, planning, and rescue. Because this region has not been directly seen, careful language is necessary. Observations indicate that a distant comet reservoir exists, and long-period comets strongly support that conclusion. Models further indicate that a denser inner component is likely, and it helps explain how the Oort cloud may endure over long timescales. It remains uncertain exactly how populated the inner cloud is, how sharply it is separated from the outer cloud, and how much of the observed long-period comet supply depends on this inner reserve rather than on the outer component alone. These are uncertainties of detail, not of general picture. The broader understanding remains that the solar system possesses an enormous distant storage region of icy remnants, and that its inward parts are more securely held than its outermost margin. For an outward traveller, the inner Oort cloud marks a change in the meaning of remoteness. At the outer edge, the sun's authority is nearly surrendered to the wider galaxy. Here, that authority is still thin, but more enduring. The journey remains far beyond the known planets, far beyond direct sunlight as a practical power, and far beyond any ordinary possibility of return. Yet it is still, in a gravitational sense, recognizably the sun's domain. The traveller is not yet beyond the solar system's deepest reserve. The sun still holds this region, not with strength, but with patience. Across immense dark distance, its gravity continues to gather ancient fragments into a vast and silent inward sea. In the deep distances of the Oort cloud, motion around the sun still exists, but it no longer resembles the orderly planetary circling familiar from the inner solar system. Here the paths are vast, elongated, and slow beyond ordinary comprehension. The sun still governs them, yet it does so from such range that the meaning of an orbit changes. A body may remain bound to the sun while taking hundreds of thousands, millions, or in some cases tens of millions of years to complete one circuit. NASA notes that some Oort cloud comets can take as long as 30 million years to make a single trip around the sun. That fact alone shows how far the ordinary language of travel begins to fail in this region. Motion continues, but it unfolds on timescales far beyond any direct human experience. An orbit is not a road laid out in space. It is a gravitational path determined by speed and position under the pull of a central mass. In the inner solar system, planets follow nearly circular paths with regular periods. In the distant Oort cloud, many paths are instead highly elongated ellipses. An ellipse is a stretched circle with two focal points, and in an orbital ellipse the sun sits at one of those points, not at the centre. This means that an object in a long Oort cloud orbit may spend almost all of its time very far from the sun, moving slowly, and then pass much more quickly through the inner regions if some perturbation brings it inward. The long path is not evenly travelled. Most of the orbital lifetime is spent in the cold outer reaches. This behaviour follows directly from the weakening of gravity with distance. The sun's pull does not end, but its strength declines sharply as range increases. When an object remains bound to the sun at great distance, it still falls inward continuously, yet its sideways motion also carries it along a path that keeps missing the sun. At extreme distance, that path becomes broad and slow. The result is a state in which the object is still under solar rule, but only loosely and gradually. The difference between bound and unbound motion becomes especially important here. A bound orbit means the object does not have enough total energy to escape the sun entirely. An unbound path means it does. In practical terms, the distinction may seem abstract because both kinds of motion can carry an object outward for immense spans of time. Yet physically it matters. A body on a bound orbit still belongs to the solar system dynamically. even if it wanders in darkness so long that return loses all practical meaning. This is one reason outward travel can become effectively one-way long before the sun's gravity becomes irrelevant. At these distances, to return is not simply to point back inward. A traveller must overcome not only distance but orbital state. If a spacecraft is moving outward on a trajectory that still remains bound, it may one day fall inward again on a timescale beyond civilization. If it is moving fast enough to escape, it will never return unless acted upon by some later force. In either case, the region teaches the same lesson. Solar gravity remains present, but it no longer offers anything like easy recall. Once motion has been established on a sufficiently distant outward path, the timescale of return separates from biological life, engineering durability, and any realistic system of support. The Oort cloud also shows that an orbit can be long without being secure. At these great semi-major axes, outside influences matter. Passing stars can alter a distant orbit. The tidal pull of the Milky Way can slowly reshape it. A weakly bound comet may be nudged inward toward the Sun, or outward toward complete escape. Over millions of years, the distinction between stable storage and ejection becomes partly a matter of accumulated perturbation. This does not mean that every distant orbit is chaotic in a simple sense. Many remain bound over extremely long intervals. It means instead that the farther from the Sun an orbit extends, the less it belongs to a purely two-body story of one object circling one star. The wider galaxy begins to participate. Long-period comets reveal this clearly. Many are thought to begin their inward journeys only after subtle disturbances change their distant orbits enough to lower their perihelia. Perihelion is the closest point to the Sun in an orbit. A comet can spend enormous spans of time in the deep outer cloud and then, after a galactic tide or stellar passage slightly alters its path, fall inward for a single observed visit. Some are seen only once in recorded history. Others may never return after passing through the planetary region, because planetary encounters and outgassing can modify their paths further. In this way, a very long orbit is not only long in time, it is also vulnerable to revision. For an outward human-made object, the same geometry carries a quiet finality. If it continues outward with enough speed to escape the Sun, then the one-way nature is literal. If it does not, then the one-way nature can still become practical rather than absolute. A return that would require tens of thousands, millions, or tens of millions of years is no return in any meaningful human sense. The path may still close mathematically, but it does not close for the travellers who depart. The orbit becomes a kind of separation by timescale. This region, therefore, changes the meaning of belonging. In the inner solar system, to belong to the Sun means to circle it within a world of repeated seasons, regular positions, and recoverable journeys. In the deep Oort region, to belong to the Sun may mean only that an object remains very gently tied to it across darkness so broad that the tie is nearly indistinguishable from freedom. The object is not yet fully released, but neither is it held in any active or protective way. The Sun remains the source of gravitational identity, yet that identity has become stretched across such immense duration that it no longer resembles residence. Long solar orbits are not dramatic. They are not marked by collision or flame. Their power lies in how quietly they erase ordinary scales. Distance becomes time. Motion becomes patience. Return becomes a technical possibility emptied of practical meaning. The solar system still holds these bodies, but only across intervals so deep that to leave along such paths is, for every human purpose, to go one way. Inside the distant Oort region, and still far beyond the main belt of Kuiper Belt objects lies a different outer population of icy bodies, one less spherical, less detached, and more visibly marked by the past action of Neptune. This is the scattered disk. It is a region of trans-Neptunian objects on long, stretched, and often strongly tilted orbits. NASA describes the scattered disk as a region extending far beyond the main part of the Kuiper Belt, populated by objects that were scattered by Neptune into highly elliptical and highly inclined paths. Some of these objects move hundreds of astronomical units from the Sun at their farthest point before returning inward toward the neighborhood of Neptune. The scattered disk is therefore not a quiet shell like the distant Oort cloud. It is a dynamically excited outer region whose form records the gravitational unrest of the early solar system. The name itself describes its origin. These bodies are understood to have been scattered outward by gravitational encounters, mainly with Neptune, during the period when the giant planets shifted from their earlier positions to the architecture seen today. In this process, small icy bodies that once occupied a more compact outer disk were kicked into new orbits, rather than being left in a calm, low-inclination belt. NASA material on the Kuiper Belt notes that the scattered disk is linked to Neptune's migration, and that the classical belt and scattered populations are connected outcomes of that history. The scattered disk therefore preserves a memory of motion rather than of stillness. Its objects are not merely distant, they are displaced. Their orbits carry the imprint of an earlier planetary rearrangement that did not end in destruction, but in exile. This gives the scattered disk a character very different from the more orderly main Kuiper Belt. In the main belt, many objects remain on less extreme paths in a broad, flattened outer ring beyond Neptune. In the scattered disk, the orbits are more eccentric, meaning more stretched, and often more inclined, meaning more tilted relative to the average plane of the planets. NASA notes that many scattered disk objects are tilted by tens of degrees, and that the scattered disk makes the overall Kuiper Belt system much wider and thicker than the classical belt alone. The region overlaps with the outer Kuiper Belt but extends much farther and farther above and below the planetary plane. It is not best imagined as a narrow ring. It is better understood as a stirred outer volume attached to the Kuiper Belt, yet dynamically more unruly. The scattered disk is still part of the solar system in a clear dynamical sense. Its objects remain bound to the Sun, though often only weakly compared with the planets. Many pass near Neptune at the inward end of their orbits, and that is one reason their long-term stability can be limited. Neptune remains the dominant sculptor of this region. Its gravity does not merely stand nearby, it continues to shape the possible paths available to scattered disk objects over immense timescales. Some may remain on these stretched orbits for the age of the solar system. Others may be pushed farther outward, nudged inward, or eventually removed from the region altogether. The scattered disk is therefore not only a historical product of gravitational scattering, it remains a place where that history continues to matter. This region also helps explain some classes of comets. NASA material notes that short-period comets may originate in the scattered disk or in the inner part of the Oort cloud. That association reflects the fact that scattered disk objects occupy a middle dynamical ground between the more stable Kuiper Belt populations and the much more distant, roughly spherical Oort cloud. Their orbits are already elongated enough that further perturbations can send some inward toward the planetary region. In this way, the scattered disk serves as a transitional outer reservoir. It is not as detached as the Oort cloud, but it is also not part of the compact architecture of the major planets. It is a region where small icy bodies remain available for later redistribution. For an outward journey, The scattered disk marks a threshold in the meaning of the outer solar system. Beyond Neptune, the solar system does not end in a neat border. It broadens into populations of remnants whose orbits are no longer simple or uniform. The scattered disk shows that leaving the planetary region does not mean entering calm emptiness. Instead, the traveller enters a zone shaped by old gravitational violence, where paths have been elongated, tilted, and partly loosened from the regular pattern of the planets. The objects here are still icy remnants of solar system formation, but they are arranged by disturbance. Their presence makes the outer system thicker, wider, and less cleanly bounded than a simple picture of planets followed by empty space would suggest. The physical conditions remain intensely cold. Sunlight is weak, and the bodies are small and dark. Yet the scientific importance of the region lies not in local appearance, but in orbital behaviour. The scattered disk reveals how far the influence of Neptune extends, and how profoundly planetary migration shaped the solar system's outskirts. It also shows why a one-way outward path becomes easier to understand here. Once an object has been scattered onto a long and eccentric orbit, return is no longer a matter of simple reversal. Motion has been rewritten into a new geometry, one that may carry the object far from the Sun for enormous intervals. The outer solar system is not made only of distance. It is made of paths altered by ancient encounters, and the scattered disk is one of the clearest records of that change. Beyond Neptune lies the Kuiper Belt, the broad outer ring of icy bodies that marks the recognized edge of the planetary region. It is not the final limit of the solar system, but it is the last major, persistent belt of small worlds that belongs clearly to the same flattened architecture as the planets. NASA describes it as the outer reaches of the solar system beyond Neptune, and sometimes calls it the third zone of the solar system. ESA likewise describes it as a flattened disk of icy objects beyond Neptune. This is an important distinction. The Kuiper Belt is not a vague outer haze like the Oort cloud, nor a strongly disturbed transition like the scattered disk. It is a broad, cold, structured belt, still linked visibly to the plane in which the planets formed and continue to move. The belt begins beyond Neptune at about 30 astronomical units from the Sun, and extends outward to roughly 50 astronomical units, though its populations are not all arranged in the same way. ESA material places the belt from 30 to 50 astronomical units, and NASA's summaries describe it as a wide region containing millions of icy objects, including many bodies large enough to count among the largest small worlds in the solar system. It is far wider than the main asteroid belt and substantially more massive, though still made mostly of dispersed small bodies separated by enormous distances. The emptiness between objects remains immense, yet the belt forms a real population, a true outer zone rather than a few isolated wanderers. Most Kuiper Belt objects are thought to be ancient remnants from the early solar system. NASA describes them as small, icy, ancient bodies, and the New Horizons mission material emphasizes that they are among the best preserved samples of what the outer solar system was like soon after its formation, more than 4.5 billion years ago. Because they formed far from the Sun and have remained in deep cold ever since. Many of them are thought to have undergone far less thermal alteration than bodies closer to the Sun. That makes the Kuiper Belt not only a region of distance, but also a region of preservation. It stores material that has changed slowly and little, keeping a record of early planet formation in cold outer conditions. The Kuiper Belt is not uniform. It includes several dynamical populations, among them the classical belt, resonant objects, and bodies linked outward to the scattered disk. In the classical belt, objects orbit far enough from Neptune to remain comparatively stable over long timescales. Resonant objects, by contrast, move in orbital relationships with Neptune, completing set numbers of orbits for every orbit Neptune makes. Pluto is the best-known example of a resonant Kuiper belt object rather than a classical one. This internal structure shows that the belt is not merely a leftover ring. It is a region shaped by the gravity and migration history of Neptune, preserving both relatively calm populations and bodies whose paths are maintained by orbital rhythm. The belt is also home to several dwarf planets and other large trans-Neptunian worlds. Pluto, Haumea, and Makemake are all associated with the Kuiper belt, while Eris occupies a more distant scattered disk orbit often discussed alongside Kuiper belt populations. NASA and ESA educational material both use Pluto and other large icy bodies to illustrate the scale of the region and the diversity of objects it contains. Some are small dark remnants, others are large enough to become round under their own gravity. Some have moons. Some show surfaces rich in methane, nitrogen, or water ice. Together they reveal that the outer planetary region is not a barren edge, but a population of worlds in miniature, each moving through weak sunlight under the distant rule of the sun. For an outward traveller, the Kuiper belt carries a special clarity. This is the region where the solar system still feels visibly organized by the same flat disk that produced the planets. The sun is weak, but the architecture remains legible. Neptune still defines the inner boundary. Many objects still share the broad planetary plane. Motion is slow, but it is recognizably part of the same original system. To cross the Kuiper belt is therefore to pass through the last major zone where the solar system's formation as a flattened disk remains plainly written into space. Beyond it, the structure becomes more scattered, more disturbed, or more spherical. Here, the old shape is still present. The belt is also closely connected to the story of comets. ESA and NASA both note links between Kuiper belt objects and short-period comets. In this sense, the Kuiper belt is not only a static archive, it is a source population. Some bodies are perturbed inward over time, becoming active comets when solar heating begins to affect their surfaces more strongly. This means the Kuiper belt participates in a slow exchange between the distant outer system and the inner planetary realm. It supplies material inward, even while it remains mostly remote and cold. The belt is therefore both a storehouse and a feeder, a deep outer reserve that still sends occasional messengers sunward. Yet the dominant impression of the Kuiper belt is still one of quiet persistence. It is ancient, cold, and broad. Its objects do not form a smooth wall, and a spacecraft passing through it would not see a crowd of worlds filling the sky. The distances between objects are far too great for that. But scientifically, the belt is dense with meaning. It marks the outer boundary of the major planetary arrangement. It preserves primitive material. It records Neptune's influence. It contains dwarf planets and building blocks alike. And it shows that even at the recognized edge of the planetary system, the solar system does not end abruptly. It thins, broadens, and transitions. In the Kuiper belt, the one-way character of leaving the solar system becomes easier to feel in physical terms. A journey outward has already crossed beyond the last giant planet and entered a realm where the sun's warmth is faint and resupply is no longer imaginable. The traveller moves through an ancient ring of icy remnants that still belong clearly to the solar system, yet already stand far beyond ordinary return. The belt is not the end. It is the last broad, organized outer zone before the solar system loosens into deeper and more tenuous distance. Within the deep cold beyond Neptune, a small number of worlds stand out from the surrounding multitude of icy bodies by size, shape, and complexity. These are the dwarf worlds of the outer solar system, the large trans-Neptunian bodies whose gravity has drawn them into rounded or elongated forms, and whose surfaces record long histories of freezing, irradiation, collision, and slow evolution. NASA's current overview of dwarf planets identifies Pluto, Haumea, Makemake, and Eris as major outer system dwarf planets associated with the Kuiper Belt and related trans-Neptunian populations. Pluto lies in the Kuiper Belt. Makemake and Haumea are also Kuiper Belt dwarf planets. Eris is of similar scale, but on a more distant scattered disk orbit. Together, these worlds show that the outer solar system is not only a belt of fragments, it also contains full worlds in miniature, each preserving a different version of life at the edge of sunlight. Pluto is the most familiar of these bodies, and still the clearest example of how much activity and diversity can persist at great distance from the Sun. NASA states that Pluto is a dwarf planet in the Kuiper Belt, and that the New Horizons spacecraft became the first mission to explore it up close in the year 2015. That flyby revealed a world with nitrogen, methane, and carbon monoxide ices, mountain ranges of water ice, a layered atmosphere, and signs of active surface renewal. In scientific terms, Pluto is not merely a frozen relic, it is a differentiated world, meaning that its interior and exterior have separated into distinct layers rather than remaining a uniform mixture. Even in weak sunlight, it retains enough internal history to produce geology. Its existence shows that distance does not automatically mean simplicity. Haumea presents a different kind of outer world character. NASA describes it as one of the fastest rotating large objects in the solar system, and notes that it is the first known Kuiper Belt object found to have rings. Its rapid spin gives it an elongated shape, unlike the more rounded forms of Pluto or Eris. It also has 2 known moons. Haumea therefore reveals that dwarf worlds in the outer solar system are not all built on one plan. Rotation, collisions, and internal composition can shape them very differently. A fast-spinning body in such a distant region preserves evidence of old impacts and angular momentum that have not been erased by thick atmospheres or strong solar heating. It remains a cold world, but not a simple one. Makemake is another large icy world of the Kuiper Belt, slightly smaller than Pluto and described by NASA as the second brightest object in the Kuiper Belt after Pluto. Its brightness reflects a surface rich in frozen volatile compounds, especially methane ice, and it stands as an example of a large world that is still strongly shaped by deep cold and surface frost chemistry. NASA's current Makemake page places it firmly in the Kuiper Belt with Pluto and Haumea. Although it is less well known than Pluto, Makemake helps define the broader population of large outer dwarf worlds that preserve early solar system materials while also developing their own surface histories. It is a quiet body, but not an empty one. Its existence broadens the picture of the outer architecture by showing that Pluto is not unique. Eris lies farther out still, on a path associated with the scattered disk rather than the main Kuiper Belt. NASA notes that Eris is about the same size as Pluto, but around 3 times farther from the Sun on average. Its discovery helped trigger the debate that led to the formal clarification of the planet definition in the year 2006. Eris matters scientifically because it demonstrates that large worlds exist beyond Pluto, and that the outer solar system extends into populations that are not arranged in a simple ring alone. Its distance also underscores how weak sunlight has become in this region. A world of roughly Pluto's scale can orbit in darkness so deep and remote that it lies far outside the most familiar outer system imagination, yet it still remains clearly within the Sun's gravitational system. Together, these dwarf worlds reveal the architecture of the outer solar system more clearly than a belt of small bodies can do by itself. They mark the fact that beyond Neptune, the solar system still contains discrete worlds with geology, atmospheres in some cases, moons, rings in at least one case, and diverse dynamical histories. NASA's Kuiper Belt overview describes the region as containing millions of icy objects, including many larger than 100 kilometers across and some over 1,000 kilometers wide. The large dwarf worlds are therefore the visible peaks of a much broader population. They are not exceptions in an otherwise empty space. They are the largest representatives of an ancient outer system that never became a full set of major planets. For an outward traveller, these worlds also have a narrative importance. They are the last places where distance still condenses into recognizable planetary forms. Beyond them, the solar system continues, but it becomes increasingly sparse, abstract, and hard to imagine as a place of worlds. Here, even in profound cold, there are surfaces, horizons, moons, and physical landscapes, yet those landscapes already lie so far from Earth and from useful sunlight that they belong to a domain of extreme isolation. To pass these dwarf worlds is to move through the final realm where the outer solar system still offers individual worlds instead of only reservoirs and populations. Their quiet presence clarifies the one-way nature of the journey. These are not stepping stones homeward. They are markers of how far the Sun's family extends while still remaining bound to it. Weak sunlight, long orbital periods, and great separation from one another make them poor candidates for rescue, support, or return. They are worlds, but they are worlds at the threshold of practical irreversibility. The outer architecture is still readable here, yet already stretched to the point where departure becomes less a voyage through destinations and more a passage into enduring distance. Neptune is the last major planet in the solar system, and the final dominant gravitational world along the broad outward path from the Sun through the planetary system. Beyond it, there are belts, dwarf worlds, scattered populations, and distant reservoirs. But no other major planet remains to define the architecture in the same commanding way. For this reason, Neptune forms a kind of gravitational gate. It does not create a physical barrier, and it does not mark the end of the solar system, but it does stand as the last great planetary mass whose orbit, motion, and gravity shape the structure of outward travel in a direct and lasting way. To pass beyond Neptune is to leave behind the final major world of the Sun's planetary order. Neptune orbits the Sun at an average distance of about 30 astronomical units. At that range, sunlight is already reduced to a faint fraction of what reaches Earth. The planet moves slowly through deep cold, taking about 165 Earth years to complete a single orbit. Its distance and period alone make clear that the outer planetary region is governed by a different scale of time. Neptune does not circle the Sun in a rhythm that belongs to human history. It belongs to a slower outer tempo in which years become generations, and one full season on a planet can exceed the span of a civilization. Yet despite this remoteness, Neptune still acts strongly on the space around it. It is not an isolated ornament at the edge of the solar system. It is a gravitational authority. That authority comes first from mass. Neptune is far less massive than Jupiter, but it is still a giant planet, with enough gravity to control moons, retain a substantial atmosphere, and shape the orbits of smaller bodies far beyond its own visible disk. In the outer solar system, where the Sun's pull is weaker than it is closer in, planetary gravity can redirect small bodies more effectively relative to the background environment, Neptune's role in shaping the Kuiper Belt, resonant populations, and scattered disk is one of the clearest examples. Many objects beyond Neptune are not simply placed where they formed. Their present paths reflect Neptune's long gravitational influence, whether through resonance, scattering, or slow orbital confinement. A resonance is a repeating orbital relationship between two bodies. In such a relationship, one object completes a specific number of orbits while another completes a different specific number, and the repeated pattern helps maintain or reshape the smaller object's path. Pluto, for example, is locked in a stable resonance with Neptune. This means Pluto and Neptune never collide even though their paths, viewed simply by distance from the Sun, might appear to cross. Neptune therefore does more than occupy the outer planetary lane. It organizes nearby orbital space. It creates regions of stability and instability, preserving some paths while disturbing others. This is one reason Neptune serves as a true gate. To move beyond its realm is not merely to go farther from the Sun. It is to move beyond the last major system of planetary orbital control. For spacecraft, Neptune has another importance, though one that belongs more to possibility than to history. The giant planets can alter the paths of passing objects through gravity assists, also called gravitational slingshots. In such a maneuver, a spacecraft passes near a moving planet and exchanges momentum with it, changing speed and direction relative to the Sun. Voyager 2 used Neptune for such a flyby in the year 1989. Though its mission design was built around a rare alignment of the outer planets and did not depend on Neptune alone for its outward escape. Even so, the principle matters. Neptune is the last planet from which a spacecraft can gain or lose meaningful heliocentric speed through direct planetary encounter. Beyond Neptune, no larger world remains to perform that role. The traveller who has passed the orbit of Neptune has also passed the final major chance for planetary redirection. This gives Neptune a special place in the story of one-way journeys. Inside its orbit, the solar system still offers repeated opportunities for gravitational shaping by large planets. A spacecraft can cross the domains of Jupiter, Saturn, Uranus, and Neptune, each one able in principle to alter the path. Outside Neptune, outward travel becomes much more dependent on the speed and direction already acquired. There are still smaller bodies and distant populations, but no major planet stands ready to revise the trajectory in the same sweeping way. In this sense, Neptune is the last great editor of outward motion. Once its realm is behind, the journey becomes more final in its geometry. Neptune also marks the last major world around which the solar system still presents itself in a recognizably planetary form. It has an atmosphere rich in hydrogen, helium, and methane. It has strong winds, active weather, a system of rings, and a large moon, Triton, which itself is likely a captured Kuiper Belt object. This means Neptune stands not only as a boundary of orbital mechanics, but also as a boundary of planetary richness. Outward from Neptune lies a colder, more fragmentary domain. There are still worlds, but they are smaller, dimmer, and less dominant. Neptune is the outermost point at which the solar system still gathers itself around a giant planet with a full planetary system of its own. Its role in the history of the outer solar system is equally significant. Models of planetary migration indicate that Neptune once moved outward from a more inward original position. In doing so, it helped sculpt the Kuiper Belt and scatter many small icy bodies into new orbital classes. This outward migration left signatures that are still readable in resonances, orbital inclinations, and the existence of the scattered disk itself. Neptune is therefore not only the last giant planet in the present arrangement, it is one of the chief makers of the outer structure now seen beyond it. The gate was not merely placed there, it helped build the region outside the gate. For an outward traveller, crossing beyond Neptune means leaving behind the last planet able to command the route in a major way. The Sun still governs the larger system, and gravity still reaches far beyond. But the planetary order has thinned decisively. No greater world remains ahead to offer assistance, deflection, shelter, or return. Neptune's orbit is therefore not the end of the solar system, it is the end of the major planets. That is enough to make it a turning point. Beyond this final giant, the outward path enters a realm where distance deepens, sunlight weakens further, and the one-way character of departure becomes steadily more complete. Between Neptune and the inner planetary system lies the long domain of the giant planets, a region where outward travel is shaped again and again by moving gravitational wells of exceptional size. Jupiter, Saturn, Uranus, and Neptune do not simply sit at intervals along a route. Each one bends surrounding space through mass, carries its own orbital momentum around the Sun, and alters the paths of smaller bodies that pass within reach. Taken together, they form the great gravitational machinery of the planetary solar system. Any object leaving the inner regions and heading outward must cross this machinery. The result is that departure is never a straight release into emptiness. It is a passage through 4 successive systems of control, each one capable of redirecting motion, changing speed, and rewriting what the outward journey becomes. A gravitational well is a simple way to describe how mass shapes motion. A more massive body creates a stronger field, and nearby objects move in response to that field. Around the giant planets, this influence extends far beyond the visible cloud tops and ring systems. Each planet has a region in which its gravity dominates over the competing pull of the Sun for nearby motion. This local domain governs moons, rings, and temporary captures, but it also matters for passing spacecraft and small bodies. When an object approaches one of the giant planets, its path relative to the Sun can be changed significantly. This is not because the planet creates energy from nothing. It is because the planet itself is moving around the Sun, and under the right geometry, some of that orbital motion can be exchanged. This is the basis of the gravity assist. In a gravity assist, a spacecraft falls into a planet's gravitational field and then climbs back out. But because the planet is moving, the spacecraft can leave with a different speed and direction relative to the Sun than it had before. NASA's flight dynamics descriptions make clear that the key is the 3-body nature of the event: the spacecraft, the planet, and the Sun. The spacecraft may gain heliocentric speed by taking a tiny amount of orbital energy from the planet, or it may lose heliocentric speed if mission design requires slowing inward. The amount taken is negligible for the planet and transformative for the spacecraft. In outward missions, the giant planets therefore become gates of acceleration. Jupiter is the most powerful of these gates. It is the largest planet in the solar system, and by far the strongest single planetary source of gravitational redirection available to departing spacecraft. Its mass and rapid motion around the Sun make it the principal tool for sending missions outward with high energy. A well-designed pass by Jupiter can change a trajectory dramatically, lifting a spacecraft toward the outer planets or beyond. Saturn can also assist, though generally less strongly than Jupiter. Uranus and Neptune can continue to reshape a path, especially when a mission is already deep in the outer system. The 4 giants together form a sequence of possible exchanges, and in rare periods of favorable alignment, they allow outward missions of extraordinary reach. This same machinery also governs the natural history of countless small bodies. Comets, icy remnants, and planetesimals do not drift through the giant planet region unaffected. They are scattered, captured, redirected, or ejected. The giant planets are therefore not only destinations, they are dynamic filters that sort the material of the solar system. Some objects are flung inward toward the terrestrial planets. Some are cast into elongated outer orbits. Some are sent completely out of the solar system on hyperbolic escape paths, meaning trajectories that are no longer gravitationally bound to the Sun. Others are trapped temporarily or permanently into resonances and families of motion. The outer architecture described in earlier sections, including the scattered disk and parts of the distant comet reservoir, is inseparable from this long work of giant planet gravity. This means that outward departure depends not only on fuel and engineering, but on timing and geometry. A spacecraft does not simply leave Earth and aim for interstellar space in a single pure line, unless it carries enormous energy of its own. In practice, much of what becomes possible depends on where the giant planets are when the spacecraft reaches them. Planetary alignment matters because each assist depends on the moving position of the target planet in its own orbit. A useful encounter window may come rarely. The path must be planned so that the spacecraft arrives at the right place and time to borrow from the planet's motion. The outward journey is therefore partly a negotiation with the clockwork of the giant planets. At the same time, these planetary wells impose risk and finality. A trajectory shaped by a gravity assist is not easy to undo. Once a spacecraft has taken a major outward slingshot from Jupiter or another giant planet, reversing that change would require energy of comparable scale or another precisely arranged planetary encounter. The further outward the craft travels, the fewer such opportunities remain. In this way, the giant planets do not only help departure, they also help make it one way. They give the spacecraft the speed to leave, and in doing so they often place it on a path whose reversal becomes far beyond practical reach. The domain of the giant planets is also the last region where the solar system still offers repeated opportunities for large-scale path correction through natural celestial mechanics. Inside this region, a traveller can in principle use successive encounters to build or alter a route. Outside Neptune, that era is over. The journey then depends mostly on the momentum already gained. The giant planets are therefore the last great collaborators in outward motion. Their moving gravity wells are the final natural engines available to a departing craft. Seen as a whole, this region is not merely a stretch of distance containing 4 large worlds. It is the operating core of a long-range solar system travel. Jupiter provides the greatest leverage. Saturn extends and refines the path. Uranus and Neptune continue the shaping in the outer reaches. Together they form a gravitational corridor through which many outward possibilities are created and many return possibilities are quietly removed. The traveller passing through this domain is still within the planetary solar system, but already subject to forces that transform departure into commitment. By the time the last of these moving wells is behind, the outward path has become something much harder to revise. The giants have done their work, and the one-way journey has gained its decisive momentum. Inside the domain of the giant planets and outside the crowded inner system lies a broad span of solar system distance, where outward travel becomes less a matter of encounter and more a matter of persistence. Here the sun still dominates the overall motion, but the traveller is no longer constantly negotiating with the strong local gravity of major planets. The path stretches across space that is thinner in events, dimmer in light, and simpler in structure. It is not empty in an absolute sense, but it is empty in the practical way that matters to a journey. There are few opportunities, few corrections available from nature, and few landmarks that can change the outcome once a path has been set. The outward motion that began with launch and was reshaped by planetary gravity now continues mainly by inertia, which is the tendency of a moving body to keep moving unless acted upon by a force. In these middle solar distances, the Sun remains the central fact. Its gravity still controls the large shape of the trajectory. Even an object moving strongly outward is still falling under the Sun's pull. Unless it has already reached escape speed relative to the Sun, its motion remains part of a bound path, even if that path is so large that return would take spans of time beyond practical meaning. At the same time, sunlight continues to weaken with distance. This weakening does not happen gradually in the ordinary sense. It falls according to the square of the distance, which means that when distance doubles, available sunlight drops to 1/4. The effect is severe. A spacecraft that travels outward does not merely receive a little less solar energy year by year. It moves into a regime where light rapidly loses its usefulness as a power source, and warmth becomes increasingly costly to preserve. This change matters profoundly for engineering. In the inner solar system, sunlight is abundant enough that solar panels can supply major spacecraft systems. Farther outward, the same panels produce less and less power unless made larger and larger, which itself creates practical limits of mass, structure, and mission design. By the time missions reach the domain of Jupiter and beyond, solar power becomes difficult for many purposes, and other energy sources may be required. The traveller moving through these middle distances therefore enters a region where departure is no longer sustained by the Sun in an everyday technological sense. The Sun still lights the way, but it no longer easily powers the journey. Thermal reality changes as well. Space is not cold because it contains some active freezing substance. It is cold because matter far from strong energy sources radiates heat away and receives little in return. A spacecraft, habitat, or human body in these distances cannot rely on surrounding warmth. It must carry its own heat or generate it internally. The challenge is not only survival in vacuum, though vacuum remains fundamental. It is the continuous effort required to prevent heat loss, maintain systems, and avoid gradual failure in an environment where every watt becomes precious. The farther the journey continues, the more strongly this becomes a story of conservation. Communication also changes in this region, though not yet into the most extreme delays of interstellar travel. Radio signals move at the speed of light, and over growing distances the time required for messages to travel becomes measured in many minutes and then hours. This means that control from Earth becomes less immediate and more dependent on prediction, autonomy, and patience. A mission cannot be steered as though it were nearby. It must increasingly manage itself between delayed exchanges. The outward traveller is therefore separated not only by distance, but by time in communication. Each correction, each report, each failure and response unfolds with delay. The journey becomes less like operating a machine and more like setting a process in motion and waiting for reality to return an answer. This middle region is also where the scale of one-way travel becomes emotionally legible without yet becoming abstract. Closer to Earth, the solar system still feels populated by familiar planets, near enough in principle to imagine routes, missions, and eventual return. Far beyond Neptune, the distances become so vast that practical thought begins to dissolve into pure mechanics. But here, in the long span between these states, the traveller experiences the transition itself. The Sun is still visible as the dominant star. The solar system is still recognizably a system. Yet the opportunities for return are already fading. Every outward kilometre adds not only distance to be crossed back inward, but also energy that would be required to reverse momentum and climb once more against solar gravity. Motion through this region therefore becomes a matter of accumulated commitment. A spacecraft on an outbound trajectory is not simply cruising through neutral space. It is carrying the consequences of all earlier decisions: the launch energy, the orbital timing, the planetary assists, the mass carried, the fuel spent, the power system chosen, the thermal design accepted. Here, the journey becomes honest. There are fewer chances to hide an error by using a nearby planet or a fresh intervention. What was built into the mission now begins to determine its fate more completely. The physical landscape remains sparse. There may be dust, occasional small bodies, and the wide orbits of the outer planets depending on location. But the dominant experience is one of widening separation. The planetary sun-centered system begins to feel less like a neighborhood and more like a gradient fading into dark. Yet the sun's gravity still holds the motion in its long framework. The traveller remains within the solar system's central rule, even while moving beyond the reach of easy support. This combination is one reason the region is so important to the meaning of a one-way journey. The traveller has not yet left the sun behind in a physical sense, but already lives under conditions where home can no longer function as a practical nearby source of rescue, supply, or rapid command. By the time these middle solar distances are crossed, departure has changed character. It is no longer mainly an act of leaving planets behind. It has become the sustained acceptance of remoteness. The sun grows dimmer, communication grows slower, power becomes harder, heat becomes a burden to preserve, and motion depends ever more on momentum already earned. Nothing dramatic announces this transformation. It arrives quietly through distance itself. The outward path continues, and with each hour the possibility of reversing it becomes less an option and more a theoretical memory. Inside the broad middle distances, the solar system becomes more crowded, more luminous, and more demanding. This is the region of the terrestrial planets, where Mercury, Venus, Earth, and Mars move along relatively compact paths under a much stronger pull from the Sun. Here outward departure begins in earnest, not because the voyage is already far advanced, but because this inner system is where every escaping path must first fight through dense orbital motion and steep solar gravity. The traveller is still close to home by cosmic standards, yet the fundamental difficulty of leaving the solar system is already present. It begins here, in the tightly bound heart of the planetary system, where speed, direction, and timing matter from the first moment. The 4 planets closest to the Sun are the terrestrial planets, a class defined by their rocky composition and relatively small size compared with the giant planets. The inner planetary region is not arranged as a straight line leading outward. Each planet moves around the Sun on its own orbit, carrying its own velocity, and Earth itself is not standing still while a spacecraft departs from it. Earth travels around the Sun at about 29.78 kilometers per second. This means that every launch from Earth begins not from rest, but from a world already moving rapidly through solar orbit. A departing spacecraft inherits that motion. The question is not simply whether it can rise from Earth or clear the atmosphere. The deeper question is how its motion will be changed relative to the Sun. To leave the solar system, it must do more than escape Earth. It must enter a heliocentric path, meaning a path around the Sun, with enough energy to avoid falling back into a closed solar orbit. This is why the inner planetary region is a place of crowded orbital geometry rather than simple launch. Mercury, Venus, Earth, and Mars each move at different orbital speeds and distances. A spacecraft leaving Earth immediately becomes part of that geometry. If it departs in the direction of Earth's motion, it can add to its heliocentric energy more effectively. If it departs in the opposite sense, it can reduce heliocentric energy and fall inward toward the Sun. Trajectory design therefore begins with the fact that Earth is already in motion and already deep inside the Sun's gravitational well. The Sun's pull at 1 astronomical unit is still strong enough that a spacecraft must carry or acquire substantial additional energy if it is to climb outward rather than merely reshape its orbit within the inner system. The terrestrial planets also make the region crowded in another sense. Their orbits are close enough together that travel through the inner solar system remains a matter of intersecting moving paths. Venus lies inward from Earth, Mercury farther inward still, and Mars outward from Earth. Each planet occupies not only a place but also a timing problem. Windows for transfer open and close as the planets move. Even a mission that aims ultimately for deep space must first leave a moving planet within a moving system. It must depart at the right moment relative to Earth's rotation, Earth's orbit, and often the future positions of outer planets if gravity assists are planned. In this way, the one-way journey begins not with emptiness but with celestial traffic. Solar gravity is also far steeper here than it appears from a distant outward perspective. Near Earth, the Sun is not a background influence. It is the dominant central mass of the system. A spacecraft that has escaped Earth's local gravity has still done only a fraction of the larger work required for true solar escape. It may enter an orbit around the Sun that remains only slightly different from Earth's own. From there, to move substantially outward requires more energy. This is one reason deep space departure is difficult even after launch succeeds. The spacecraft is still near the bottom of the Sun's broad gravitational well, carried sideways by Earth's orbital motion and bound tightly to the Sun's inner domain. The inner region is also the place where sunlight is strongest and, in a practical sense, most generous. Solar power is abundant compared with the outer system. Communication delays are shorter. Thermal conditions, though still severe in space, are easier to manage than they are in the cold outer reaches. Yet this practical generosity can obscure the deeper truth. The ease of operating near the Sun does not mean ease of leaving the Sun. In fact, the opposite is true. The region that offers the most light and the shortest communication delays is also the region where solar gravity holds most strongly. This is part of the quiet irony of outward travel. The journey begins where support is greatest and departure is hardest. Mars, as the outermost terrestrial planet, marks the last part of this crowded rocky region. Beyond it, the asteroid belt begins and the spacing of the solar system changes character. But within the terrestrial zone itself, the pattern remains compact and dynamically busy. The planets are small compared with the giants, yet their proximity to the Sun makes the region energetically demanding. A spacecraft traveling outward from Earth must first establish itself against both Earth's gravity and the Sun's stronger central hold. If it aims for the giant planets, it does so from deep inside the system, not from a neutral middle point. This region also defines the human meaning of departure. Earth is here, and all practical support begins here. The inner solar system contains the only known inhabited world, the only present source of repair, manufacturing, and biological continuity. To leave this region is not merely to move away from one planet. It is to leave behind the compact zone in which human intervention can still be imagined on relatively modest timescales. Once the outward traveller passes beyond this rocky inner architecture, return becomes progressively harder not only in mechanics, but in civilization. The infrastructure of recovery remains concentrated near Earth. For that reason, the terrestrial planet region is not just the start of the journey, it is the last place where departure can still feel reversible. The planets remain near enough, light remains strong enough, and time delays remain short enough that motion still seems connected to human intention. But the mechanics already say otherwise. Every kilometre per second gained here determines what can happen later. Every launch choice is amplified by the sun's gravity. Every successful escape from Earth is only the first step in escaping a much larger system. The inner solar system is therefore the narrow, demanding throat through which every one-way outward journey must pass. It is bright, crowded, and familiar, but it is also where irreversibility truly begins. Earth is the practical starting point for any human journey out of the solar system, and that fact shapes the meaning of departure more than any distant frontier does. The outward path begins not in the Kuiper belt, not near Neptune, and not at the heliopause, but deep inside a gravitational well at the surface of a rocky planet wrapped in air, water, weather, and life. Earth offers everything needed for survival before launch, and almost nothing once a craft has truly left it behind. For this reason, the one-way character of the journey is rooted first in the conditions of departure. To leave the solar system from Earth is to begin by escaping not only a planet, but a planet that contains the only known environment where human beings can live without machines. Earth's gravity is the first barrier. A body at Earth's surface is held by the planet's mass, and must reach escape velocity to break free without falling back. Escape velocity is the minimum speed needed to leave a gravitational body without further propulsion, assuming no atmosphere and no later thrust. Near Earth's surface, this value is about 11 kilometers per second. That number describes only escape from Earth itself. It does not mean escape from the Sun. A spacecraft that rises from Earth and clears Earth's gravity still remains in solar orbit because Earth itself is moving around the Sun. The craft begins its deeper outward journey already travelling with Earth at nearly 30 kilometers per second around the Sun. Its future depends on how that inherited motion is changed. This is why leaving Earth is both a local and a solar problem at the same time. Rockets must first lift through the atmosphere, then accelerate enough to reach orbit or beyond, and then supply additional energy to place the spacecraft on an escape trajectory relative to Earth. After that, the craft still travels within the Sun's gravitational field. To escape the solar system entirely from Earth's orbital distance, a spacecraft must attain solar escape velocity at Earth's distance from the Sun, which is roughly 42 kilometers per second relative to the Sun. Because Earth already moves around the Sun at nearly 30 kilometers per second, a departing spacecraft can use part of that motion if launched in the right direction. Even so, the total energy required is immense. It is not enough to leave the ground. It is not enough to leave Earth orbit. It is not enough even to leave Earth permanently. The craft must be set on a heliocentric path that never closes back into a bound solar orbit. The atmosphere adds another difficulty. Earth's air is what makes life possible at the surface, yet it also creates drag and heating during ascent. A launch vehicle must fight gravity while also forcing its way through thick lower air. This demands large amounts of propellant, strong structures, careful guidance, and staged design. Most of a rocket's launch mass is propellant because so much energy is needed in the opening phase. The planet that supports human life is also the planet that makes departure mechanically expensive. A world with less gravity and no atmosphere would be easier to leave, but it would not provide the same biological home from which such journeys become meaningful in the first place. Human survival transforms the problem further. An uncrewed probe can accept long durations, low power, radiation exposure, and gradual system decline in ways no person can. A human being requires air, water, food, stable temperature, waste processing, shielding from radiation, protection from microgravity or a substitute for it, and systems reliable enough to function for years or decades without resupply. Once the mission becomes one way, there's no hidden reserve in the form of a fast return. Every life support loop must continue to work or be repairable by those on board. Every weakness in design becomes part of the traveler's environment. Deep space one-way travel for humans is therefore not only a matter of propulsion, it is a matter of sustaining a complete artificial habitat cut loose from Earth for the remainder of the voyage. Radiation is one of the quietest and most persistent threats. Beyond Earth's magnetic field and atmosphere, human travelers are exposed to galactic cosmic rays and to energetic particles from the Sun. Earth shields life from much of this through both air and magnetic deflection. A deep space craft cannot reproduce those protections easily. Shielding requires mass, and mass makes launch harder. A smaller shield reduces launch burden, but increases long-term biological risk. This balance is one reason outward human travel becomes so difficult. Earth provides protection continuously and passively. A spacecraft must manufacture protection actively and imperfectly. Time deepens every challenge. Even the nearest stars are so far away that current spacecraft speeds would require tens of thousands of years to reach them. Human travel on such timescales is far beyond present capability. A one-way journey out of the solar system therefore does not mean a near-term arrival at another star. It means departure into interstellar space with no practical possibility of return and no realistic expectation of reaching a habitable destination within a human life using present propulsion. In that sense, the journey is one way not because a law forbids turning around, but because energy, biology, engineering, and time all converge against reversal. The known artificial objects that have left or are leaving the solar system make this clear. Pioneer 10, Pioneer 11, Voyager 1, Voyager 2, and New Horizons all follow outward paths shaped by launch energy and, in several cases, gravity assists. None carries a crew, none is designed for return. They are messages of motion rather than migration. Their trajectories show what is possible for machines' long endurance, weak power, sparse communication, and acceptance of permanent outward drift. For people, the standard is much harsher. A probe can function as a fading instrument package. A human mission must remain a living world. Earth therefore defines the one-way journey in the deepest sense. It is the only place where the departure can begin, and it is also the only place whose loss gives the journey its finality. To leave Earth is to leave the atmosphere that breathes, the water that cycles freely, the gravity that shaped the body, the biosphere that repairs what machines cannot, and the civilization that supplies every hidden layer of support. A craft can carry fragments of those systems, but only as imitations maintained by effort. The farther the mission goes, the more those imitations must stand alone. In the end, leaving the solar system is one way because Earth is not portable in any complete sense. A vehicle can leave, instruments can continue, records can endure. Human beings can survive only by carrying a fragile substitute for their home into an environment that offers no forgiveness. The journey begins in light, air, and gravity at the surface of a living world, and every kilometre outward turns those conditions into memory. That is why the path is not merely long. It is irreversible in the only way that finally matters. Home remains behind, and the travellers do not truly bring it with them. The outward journey settles into a quieter meaning when all the distances have been crossed in thought. The planets fall inward into memory, one by one, from Neptune and the dwarf worlds beyond it to the giant planets, the inner rocky planets, and Earth itself. What remains is not a road between destinations, but a long separation sustained by motion and by the inability of living systems to carry their full origin with them. The solar system grows from a place into a gradient, then from a gradient into a fading source of light and gravity. The traveller continues outward, but home does not travel in the same way. The sun still shines behind, though more weakly with every passing span. Its gravity still reaches outward, though less and less strongly across the dark. Yet neither light nor gravity is enough to make return practical once distance. Time, energy, and life support have all turned against it. The one-way nature of the journey is never imposed by a wall. It emerges slowly from scale. It comes from the great cost of leaving Earth, from the power needed to escape the sun, from the loss of easy communication, from the failure of sunlight as a ready source, from the silence of interstellar space, and from the fact that biology depends on conditions too rich and too delicate to be carried perfectly into the dark. What leaves the solar system, in the end, is not a wandering extension of Earth. It is a small constructed refuge moving through an environment that does not notice it. The planets continue their orbits. The heliosphere continues its motion through the galaxy. The interstellar medium remains thin and patient. The Milky Way holds its stars at distances so large that even the nearest destination belongs more to future imagination than to present travel. The outward craft keeps moving, and the meaning of that motion becomes simple. It is departure without natural return, distance without relief, continuation without reversal. In that stillness, the journey is understood not as an act of conquest, but as an acceptance of limits. The solar system can be left by machines, and perhaps one day by living travellers, but not without surrendering the ordinary promise of coming back. The farther the craft goes, the more clearly this remains true. Earth stays where it has always been, turning in light around its star, while the traveller passes outward into a dark that has no path home,